All right, today we're going to talk about parametric relations and inverses. All right, so we got a lot of objectives here. Okay, so definition, parametric curve and a parametric equation. The graph of the ordered pairs x, y, where x equals f of t and y equals g of t. What this means is you have a function in terms of x and t, and you have a function in terms of y and t. Our functions defined on an interval I of t values is a parametric curve. The equations are parametric equations for the curve. The variable t is the parameter, and I is the parameter interval. The easiest way I can kind of explain parametric curves and parametric equations is, and we're not going to get this complicated, but just so you know where this is going, because we will revisit parametric curves later in the year. If you look at our Cartesian coordinate system, we have an x-axis and we have a y-axis. Generally speaking, whatever x represents and whatever y represents, okay? Let's take an example of maybe this car on this cliff, and he's driving this way. Now, we all know once he hits the edge of the cliff, he's going to go down. But if we didn't have gravity, okay, you could think of what's going to happen is two things are happening. This car is going to continue going in this direction. But gravity, there's another thing forming on it, which is the y-axis, and that's going to push it down. So two things are happening to this car. It's going a horizontal direction over time, and it's also going to be going down over time. So what we do is we come up with this equation, this x equation, if you will, that describes this horizontal motion of the car. Then we come up with this as in relation to time. And then we come up with this y equation, which represents the vertical motion of this car over time. That time is what we call the parameter, okay? Which allows us to look at these two motions separately, kind of, instead of just, normally we would just look at it and look at what happens. We wouldn't, obviously it's going to hit the curve and it's going to hit the cliff and it's going to go down. Normally that's what we would look at. Parametric equations allow us to look at what would happen over time if just this was happening, and what would happen over time if just this was happening, instead of what happens together. Okay, that's a very, very rough kind of example of parametric curves, and we will get way more into it later in the year. All right, but it kind of allows you, hopefully, to see what we're finding. So, steps for finding points determined parametrically. Substitute each value of t into the functions for x and y. Record the points that it determines parametrically. To eliminate the parameter, and that means to get rid of the t and get it right back into what we're used to, which is just x and y, solve one of the equations for t, substitute in the other equation, and simplify. All right, so it says consider the set of all ordered pairs x, y defined by the equations. My x equation is saying take time and add 1 to it. My y equation is saying square the time, multiply it by 2, and add those together. So it says find the points determined by t equals -3, -2, -1, 0, 1, 2, and 3. So what you do is you make this table. There's my time, there's my x equation, there's my y equation, and when I'm done, whatever I plug in for t, obviously I'll get an x coordinate and I'll get a y coordinate, and that becomes my ordered pair. Okay? So if I plug in -3 for the x equation, -3 plus 1 is -2. -3 squared plus 2 times -3, that's going to be 9 minus 6 is 3. So the ordered pair, when time is -3, is -2, 3. We plug in -2, we do the same thing. -2 plus 1 is -1. -2 squared plus 2 times -2, that's 4. Minus 4 is 0. Plug in -1. You get 0 and -1. I'm not going to do all the math. It's very simple. Plug in 0, plug in 1, plug in 2, plug in 3. And so we end up with these ordered pairs for these two parametric equations. So I'm going to get a little bit of ahead kind of and show you what's going on. Right now for A, technically we're done. but I kind of wanted to show you. Let me switch the thing. All right, we're done. We don't have to do this right now. I mean, we would have been done just with those ordered pairs. I'm just illustrating what's going to happen next. So I want to show you kind of graphically what we're going to do by hand. So if I go to my calculator and I plug in these points, these are my x points. I'm going to do a stat edit, and I plug in these for L1 and my y's for L2, and I turn my plot on and I set my window. I probably went from, looks like, -10 to 10, and I went, looks like, -5 to 20 or 50, yeah, I think 20. Okay, so that I could get all my data points in, turn the plot on, and those are the points defined parametrically by these two equations. This is a line, this is a parabola, and parametrically we get a parabola when we're done. Okay, so now if I obviously it's a quadratic because I can see the parabola there. So if I do stat calc a quad regression, it tells me that A is 1, B is 0, C is -1. If I plug those in, I get the relationship between x and y, between these two equations, is x squared minus 1. Because you do 1x squared plus 0x plus a -1, which gives me x squared minus 1. Again, we don't have to do that for A. I'm just doing it to show you what we're fixing to do next, which is, and what we just did was we eliminated the parameter. Notice that there's no more t in my equation, my parametric equation. Alright, so B says find an algebraic relationship between x and y. We just did on the calculator. Now we're going to do it by hand. Okay? And again, when you do this, when you find that algebraic relationship, it's called eliminating the parameter. And then they also want to know, is y a function of x? So what we do is you pick one equation and solve it for t. This one's going to be the simplest one to solve for t because there's only one t in it. This one has a t squared and a t. You can do it, but that's going to be a pain. So I'm picking my first equation, x equals t plus 1, and I'm going to get t alone. So to get t alone, I'm going to minus 1, and I get x minus 1 equals t. Well, now I can substitute that in to my second equation. Everywhere I see a t, I'm going to substitute x minus 1. So I would get y equals t squared plus 2 times t, but I'm plugging in x minus 1. And then simplify that. You got to make 2 copies so you don't kill puppies. Plus 2 times x minus 1. That's going to give me x squared minus x plus 1 plus 2x minus 2. That's going to give me, this is going to be negative 2x, and a positive 2x cancel out, so I have x squared plus 1 minus 2 is minus 1. And just like I got here, by hand, I got the same thing. There's the relationship between x and y. And they want to know, is y a function of x? Well, that's a parabola. We graphed it on the last page on the calculator. This would pass the vertical line test if you graphed that. So yes, it's a function. Okay? Oh, I forgot I animated that. Sorry. Alright, so then it says, consider the set of all ordered pairs x, y defined by the equation. Same thing. Working on the same problem. Now we're on C. They want me to graph the relation in the xy plane. Again, we already did that. Alright? I already had my points in, remember? So now what I'm going to do is I'm going to go leave the plot on so it'll still plot your points, but next to y you're going to type x squared minus 1. Sorry, I took a picture of that and it blocked it out. So I'm going to type in x squared minus 1. And notice that it hits all of my dots. So it's a really good fit for my data. And you can see that it passes the vertical line test. So yes, it's a y is a function of x. Okay? Alright, you try this one. Hit pause. Come back when you're ready. And hopefully you got 12, 7. They want me to find the ordered pair for when t is 4. So for the x equation, I change t to 4, and I get x equals 12. For y, I change t to 4, and I get 16 minus 9, which is 7. So that ordered pair when t is 4 is 12, 7. Okay? Try this one. They want you to eliminate the parameter. Hit pause, come back when you're ready. And hopefully you got 4. Alright, I'm going to pick this equation and get t alone, because it looks the simplest. So to get t alone, I'm going to add 5. And I get x plus 5 equals t. So now I'm going to substitute in for the other equation. So y equals t squared minus 6 times t. But I got to plug in my t, which is x plus 5. And then simplify. Make 2 copies so you don't kill puppies. And I'm going to distribute here. So minus 6x minus 30. X squared plus 5x plus 5x plus 25 minus 6x minus 30. I got x squared. I got 10x, take away 6x is positive 4x, and I got 25, take away 30 is negative 5. So there's my relationship between x and y. Alright, so how are relations defined parametrically? You have an x equation as a function of time, and you have a y equation defined as a function of time. And then you get those x, y ordered pairs. How do you graph parametrically defined functions and relations? You find the x, y pairs and you graph them. How do you eliminate the parameter and write y as a function of x? Oops. Sorry. I hate it when it backs up on me. Come on. You solve one equation for t. Sub into the other. And simplify. Okay? Alright. So, to use a graphing calculator in parametric mode, you're going to go to mode. Hit your mode key. I should have put a picture of the calculator up here. You click on your mode key, and then in the 4th row down, choose PAR. These are your choices: function, parametric, polar, and sequence. We'll do all of them eventually except for sequence this year. Function is what we're normally in if you're talking about equations in x and y. Parametric is when you have x and y equations in terms of t. Anyway, choose parametric and make sure that's black. And then when you go to y equals, it's going to look different. Your screen's going to look funny. Instead of just having y equals, it's going to have x1 of t equals and y1 of t equals. Type your x equation for x1, type your y equation for y1. Make sure you go to set your table set, alright, to fit your data. And then we could go to table and see the points instead of having to figure them out algebraically by myself. Okay, so to graph, remember you gotta have to set your window. You're gonna set your t min according to the t equation and your t max according to the equation. Set your x and y mins and maximums according to your data, and then hit your graph key and sketch the graph. Alright, so we have these two. Consider the set of all ordered pairs defined by these two equations. A says use a graphing calculator to find the points determined by t equal negative 3 to 3. So if you have your mode all set, alright, here's what I was talking about a while ago. When you hit mode, you have these choices. You want to make sure parametric is black. And then your screen looks like this now. So for x1, I type in, and oh, notice, dang it, I didn't put the key on. The same key that you hit to get an X, when you hit that key now, it'll type a T for you. Don't do the alpha T. I don't know if you can or can't, I don't know if it'll work or not, but don't use the alpha key. You just use the same key you would use to type an X. It's just that when you're in parametric mode, it types a T instead of X. If you're in polar form, it types a theta instead of x. In sequence form, I don't even know what the sequence form does. I don't use that one. All right, but at any rate, just use your x key and it'll type a t for you. So you type in your x equation for x1, your y equation for y1. Okay, I'm going to do my table set, and I'm going to make it start at -3 because it wants me to find the points from t equal -3. So I'm telling my table to start at -3 and count by ones. And then when I hit my chart, you can see, all right, there's just like we did algebraically, when t is -3, x is 3, y is -2. So that ordered pair is going to be 3, -2. When t is -2, x is 0, y is -1. That ordered pair is going to be 0, -1. And so on and so forth. Okay, so you see how we end up with our xy ordered pairs using the graphing calculator. Okay, so we've got our points. Now B says use a graphing calculator to graph the relation in the xy plane. You already have these typed in. We just need to set our window. I don't really know why I set it at -10, but I set my t-min at -10 to go to 20, and I stepped by ones. My x-min, because my data, remember, was I started at -3 and I went to 20 and counted by ones. And my y-min, I went from -3 to 10 and I counted by ones. And you're going, well, Miss, how'd you know to use those? I didn't. I probably tried a standard window and didn't see a good picture, so I probably just played with it until I got a good picture. At any rate, this is what you get. Okay? And then they want to know, is y a function of x? Well, it doesn't pass the vertical line test, so no. Okay. D, find the algebraic relationship between x and y. If I'm doing it algebraically, I'm going to pick one equation and get t alone. I'm going to pick the y equation this time because it's simpler. So to get t alone, I'm going to -1, and I get y minus 1 equals t. So now I'm going to plug that in to my x equation. So I'd have t squared plus 2 times t, and my t is y minus 1. So if I simplify that, 2 copies so I don't kill puppies, distribute the 2, I get 2y minus 2, y squared minus y plus 1 plus 2y minus 2. This is -2y plus 2y cancels, and I get y squared minus 1. And that's what x equals. Okay? Oh, but if they want y alone, if I was to get y alone, which is, standard form, I'd add 1, so that would give me x plus 1 equals y squared, square root, and I get y equals plus or minus the square root of x plus 1. And we know that that is a sideways parabola. So if you only did the positive one, you'd only get the top half, but the plus and minus 1, you get that picture that we got. So if you went back to function mode, and you went to y equals and typed square root of x plus 1 and y2 equals the negative square root of x plus 1, you will get the exact same picture that you see here. It'll actually be a little smoother. Parametric is a little rough, alright? But if you type it in function mode in x and y, you get that same parabola, but it'll look a little smoother. Alright. So, yeah, we've already answered this. Alright, so an inverse relation. The ordered pair AB is in a relation if and only if the ordered pair BA is in the inverse relation. You know, we've talked about inverses before, and normally when we found inverses, we switched x and y and got y alone. Well, they're saying the same thing. If you want an inverse of an ordered pair, switch them. Okay, we've worked with the vertical line test since a long time, okay? This would pass a vertical line test. And I'm sure you've always wondered, is there a horizontal line test? There is. We just really didn't need it until now. The horizontal line test, it says, the inverse of a relation is a function if and only if each horizontal line intersects the graph of the original relation in at most one point. So it's the same concept as your vertical line test, but what it tells you, it doesn't tell you if the relation is a function or not. It tells you whether its inverse will be a function. So in my example, my parabola is a function. Its inverse, however, will not be a function because it doesn't pass the horizontal line test. Okay? Now, they're going to talk about a function being one-to-one. A function is considered one-to-one basically if it passes the vertical line test and the horizontal line test. If it passes both, then the function has an inverse that's a function. If it fails one or both of the tests, then it's not one-to-one and does not have an inverse that's a function. Okay? Alright, so it says, A, find the relations that are functions. Functions mean, relations or functions is just vertical line test. This passes, so yes. This does not pass, so no. This does not pass, so no. This does pass, so yes. Okay, so these two are functions, these two are not. Same graphs, and I want to know which ones have inverses that are functions. Well, if they pass the horizontal line test. So this passes, so yes. This passes, but it's not a function. It's not one-to-one because it didn't pass the vertical line test. This doesn't pass either one. This passes. Nope, this does not pass. So no. So the only function that has an inverse that's a function is this one. Okay? Alright, so how do you use the horizontal line test to determine if a relation has an inverse that is a function? Each horizontal line can only touch once. Alright, so we're at homework, which means we are done. Happy homeworking, and I will see you next time.